checked at the last moment, and there was no revision, and now I find some mistakes on my title. So it should be extremal problems concerning graphs containing neither a complete graph nor a complete bipartite graph. In 1941, Turan raised the following problem. When t and r's are positive integers which satisfies these conditions, determine the maximum number of edges of a graph of order n that does not contain the complete graph kt as a subgraph. And he showed the answer. After this kind of problem is called the Turan type problem. And the kt, which is not allowed to be a subgraph, is called forbidden graphs. So we can say this problem is a Turan type problem forbidding kt. In 1950, Jarankiewicz raised the Turan type problem, which forbids complete bipartite graphs. And in 1994, Brody and Mellendorf raised the following Turan type problem, which forbids complete graph kt and complete bipartite graph ktt together. When n is less than 2t, of course, ktt cannot be contained as a subgraph anyway, so problem 2 reduces to Turan's problem. And when n is 2t, Brody and Mellendorf showed their answer in that paper. So I tried to solve for the next instance. N is 2t plus 1, but it was not that easy, so I raised another Turan type problem, which forbids complete graph kt and complete bipartite graph kt and n minus t. So when n is 2t, actually that problem is same with Brody and Mellendorf's problem. And I solved out that problem on that paper. And by using that, I could solve out the Brody and Mellendorf problem for n is 2t plus 1. And after that, in 2005, Gyuri and me raised the following Turan type problem, which forbids complete graph kt and complete tripartite graph kttt. And we also got the answer for n is 3t. So this is the answer of a Turan problem. That number of h is n choose 2 minus summation of ni choose 2, where ni is a partition of n into t minus 1 integers, and they are as equal as possible. And in this case, we call the graph which has that many edges as the extremal graph, and in this case, the only extremal graph is kn1 up to nt minus 1, which is complete t minus 1 partite graph. Brody and Mellendorf's answer is as follows. And when they solve it, they use the complement of the graph. And I found that this is quite easy way to deal with for me, so I solved out all the other problems in terms of complementary forms. Let me introduce some notations. When G and H are graphs, G union H means just the disjoint union of G and H. So simple example is just if you have K2, K3, that means just this kind of graph with 5 vertices and edges like this. And G U plus H means a join of G and H. So you have disjoint union of G and H, and then you choose one vertex of G and one vertex of H and just put an edge in between them. So you can choose any vertex of G and any vertex of H. Okay. G minus H, which is just the difference. I will abuse the notation. I will sometimes just use that one, G minus 1 H E, or G minus 1 vertex V, that way. When n, m, and k's are positive integers, mg denotes n disjoint copies of G, and special graphs are denoted by using some notations. P denotes path, T denotes tree, and C denotes a cycle. And subscripts are all the order of M, which are the number of vertices. And if you have some more edges on G, say you have K more edges on G, then we denote it by G K star. Especially when K is 1, we just denote it by G star. Unicyclic graph is a graph with a unique cycle, so you can get it by adding one edge on tree. Okay, KT, which I already have talked about, that denotes complete graph of order T. And Kn1 up to Nt, that's complete T-partite graph with parts of order N1 up to Nt. Well, I said Brady and Mellendorf solved their problem by using complement of the graph. Here comes the definition of complement of a graph. If you have a graph G, its complement is denoted by G over line. And G over line has the same vertex set with G. And the complement of H set of G, that means the H set of G over line is the complement of H set of G. And in this talk, we just think about simple graphs. So we'll know that what I mean by complement. So if I say one more words, then if two vertices in G are connected by an edge, then they are not in G complement, and vice versa. Independent set is a subset of vertex set where no two of its vertices are joined by an edge. And IG denotes the maximum cardinality of an independent set of G. And bisectable graph is a disjoint union of subgraphs of equal size. I'm sorry, M is odd, this is misprint. It should be down, the next line. So we talked about unicyclic graph. And in the next lemma, we got, no, not here. We got the lemma which says that the independence number of a unicyclic graph is at least the floor of half of its order. So if we have a unicyclic graph, it should be half of its order, its cardinality, which they say if it has order n, then it should be like that. And if you have a tree component of order n, then it should be at least like this. So if we have m, it should be m. So for unicyclic graph, I differentiated notations. So if this equality holds, then I denoted this component as hm. In the other cases, for inequalities, I denoted the component by f odd m. And if m is even, I just denoted everything by fe m. also, I sometimes use the notation FM just to mean FOM or FEM. And LM denotes FM or FM K stars. So by adding some edges on HM, you denote those family by LM. So it might be HM or HM K star, whatever K is. And RM denotes FOM or FOM K star. And SM, FEM, or some component with some more edges added on. Yeah. Okay. So, if you look at Turan's problem, you want to find the maximum number of edges of a graph. Then it's, of course, n choose 2 minus maximum that one. So if you think in terms of its complement, you want to find the minimum number of edges. And if G did not contain KT, then its complement is an independent set of order T. So the same condition means IG bar is less than T. So Turan's problem turns out to be the problem which finds out minimum number of edges of a graph that does not contain an independent set of T vertices. And the answer is like that. And the equivalent and Brody and Mellendorf's problem in terms of complementary form the original graph does not contain KT, so then your IG, the complement of the graph has an independence number less than T, and the original problem does not contain KTT. There's a graph like this. You have T and T. So then G does not contain this kind of graph where connected and some edges might be here. These kind of graphs are all disallowed. Then in terms of G bar, the graph does not contain a graph like this one. So that's called the bisectoral subgraph of order T. Order 2T, I'm sorry. Actually, this bisectoral subgraph of order 2T is just a union of subgraphs of order T and T. So, actually, I should write order T and T rather than order T and n minus T. There. And that was their answer. And my problem, G does not contain KT nor K when KT and n minus T, especially when n is 2T plus 1, G does not contain KT nor K, T, and T plus 1. So in terms of a complement of the graph, G does not contain an independent set of T vertices, and G does not contain a subgraph which is a union of subgraphs of order T and T plus 1. And that is my answer. Where did I get this number? Actually, what I did was I just considered the first problem at first. So now in terms of a complementary graph, Ig is less than T, and G does not contain this kind of graph. It's separate. So I considered just the first condition, then it turns out to be the Turan's problem, and the answer is, and I choose T, where T and I is as equal as possible. So we have 2T plus 1, and if we divide it into T minus 1, we have 3 mores. So then we have 3, 3, 3, and all 2's. Those are ni's. And the extremal graph is just 3K3 and T minus 4K2. And at this time, E is 9 plus T minus 4. But unfortunately, if you think of this graph, this contains that kind of graph. And this time, one is of order T and the other one is of order T plus 1. One is odd number, then the other one is even number. So I try to modify that graph. And the simplest one is just to try to get joins of these components. Until I got a component of order at least T plus 2 that will be safe enough. And actually, at that time, E was that number, what I got. And I could prove that that was really the answer. So I got that kind of, I got some external graphs also. So let me try to show the proof of this answer. As I said, when you have a tree component, their independence number is at least of that size, and you have a unicyclic graph, you have also that ones. And if you have some components where you added some edges on 3 components or unicyclic components, then you have that kind of lower bounds of independence numbers. Let me introduce some notations. G bar denotes the number of vertices of G, which is the order of G. And you label 3 components of G in that way, so T1, T2 in that way, and their orders are decreasing. And all those 3 components order, so sums, TG denotes the summation of orders of those 3 components, and sharp tau TG means the number of 3 components of G.
What is 3 components?
If you have some 3 components in G.
Ah,
yeah.
don't care about any
That's right. And this is a Pigeonhole theorem. If you have m numbers, m positive integers, which sums up to b, and if m is bigger than half of b, then all the positive integers k, which is at least at most b, can be a partial sum of those AIs. And I used that Pigeonhole theorem in the next form. So if you have, if the summation of orders of 3 components is less than 4 times the number of 3 components, then any even number, which is at most the summation, is a partial sum of those orders of 3 components.
Can you show some examples?
Maybe strange notation. So if G is what? Like this. So K3, T minus 4, K2. Okay, these are 3 components. Well, actually this is not that good. Maybe I can say P3. Okay. So then you have 3 components, K2 and P3. And that one has order 3, the others has order 2. So then you say P1 is P3, and T2 is K2, and T minus 5 is K2. That way. And tau G is orders of these.
T minus 5 or T minus 3?
T minus 3, yes, thanks. That one is up to so it's 3 plus T minus 4 times 2. And sharp tau G is the number of these components, so that's T minus 3. And did you want some example of that lemma, or?
So the lemma says that you can find any number less than T minus 3.
Yeah. Well, it's like if we look at the above Pigeonhole theorem, A1 up to AM, and these all adds up to B, and M is bigger than this. So then certainly you have at least one number of order 1. Because the number of integers is bigger than half of that one. So there is some AJ, which is 1. And then, well, maybe we can denote it in its increasing order in that way. So then A1 is 1, you can say. And AJ should be at most to A1 plus AJ minus 1 plus 1, I guess, for any J. So then there is no gap if you add up those numbers. So then you can make any, so you can prove this one. So that means A2 is almost 2. then 1 is a partial sum, and 2 is a partial sum. And then you can do the same job. So 3 is going to be a partial sum, and all the numbers up to b is going to be partial sum, actually. And for the next lemma, the summation is less than 4 times the number of those components, then the average is less than 4. Then there should be a component of order 2. And then you can go on. So let's say TJs are all even components, so then their order is like a 2A1, 2AJ. And then tau G is like a 2 of AJ. So you can say that this is 2 of B. And then 2 of B is less than 4 times M. So the same with like this condition. So then any even number which is M most to that one, any 2K which is M most to 2B, that means K is M most B. Then K is, by the P-general theorem, some AJ. So then 2K is 2AJ. So it's summation of this. Okay, this one I don't need today. So the proof of this theorem for T is odd. Let's say if, okay, there are 2 things we must prove. First thing is the minimum number is the one which I stated there in the theorem. And the second one is extremal numbers. All the extremal numbers are also the ones which are stated in the theorem. So the first job is to show that E is half of 3t plus 7. And second job is when E is then G are those ones. And to prove these 2, I first assume the second part and then show first part. And then I prove the second part because this part is more complicated to prove. So I assume the second part, and then I try to prove the first part. So if it's not assumed that it's not true, so this is not the minimum number, then E is at most half of 3t plus 5, which is less than that number I picked up. And also, G of course satisfies all the conditions. Now, if we have that kind of graph G, we add some edges on G. So if graph satisfies all the conditions, that means Ij is less than T and G does not contain union of this graph, and E is, I don't like that. If there is that kind of graph, then add some more edges. And get a graph. This is G, and you get G plus and G double plus. To get these many edges. And you add the edges, then if you add the edges on the graph, the independence number will be reduced, but not be increased. So IG plus is still less than T. IG is less than T. And G does not contain this kind of graph. If you added some edges, it of course does not contain that kind of disjoint unions, because you might add some edges here, it does not affect at all. You might add some more edges here, then it of course would not contain that kind of separable parts. So these all satisfies that kind of conditions. So then, because we assume the second part, this G++ must be those extremal graphs which I stated in the theorem. So from there, we think about the G+. So G++ is one of those two graphs, that one or that one. And G plus is the graph which we can get by subtracting one edge from G++. So we can subtract an edge from G++. So if G++ is of that form, if we subtract an edge from K2, then IG plus is T, which is a contradiction. If you subtract from A, then that A minus H is going to be of that form, because A is like that. So if you subtract one H, it's going to be like that. So also in that case, by using the lemma, IG is at least T, so that's contradiction. Okay, I'm sorry. Some mistake. There are two cases, A minus H. If it's connected, then it's going to be HT plus 2 star or FT plus 2 star. In that case, we have two big independence number. And if it's disconnected, then this is going to be disconnected. So say HT A minus H is going to be disconnected with two parts, and that adds up to T plus 2. Then T is odd, so one of these is odd. So you have B and some K2 as much as you need here. T minus B minus star together. That will compose a part of size T. And you'll have the other part, then they are separated. So that's also a contradiction. And if G double plus is 3K3 union T6, then you can do the same job. So you prove the first part under the assumption of the second part. Now you need to prove the second part. So if your G satisfies those conditions and your G has that many numbers of edges, now the number of tree component is number of vertices, at least number of vertices minus number of edges. So you have at least that many tree components. And also by that, also another form of pigeonhole theorem says you have at most half of t minus 1 components of even order, because otherwise you will have some parts which are of order which is multiple of t plus 1. And in this case, because n is 2t plus 1, that component should be of order t plus 1. So we have that kind of separable union. So that's a contradiction.
So is 2t plus 1 the number of vertices in the tree component? Or?
Number of tree components of even order. Because say you have at least half of t plus 1 components, 3 components of even order, and you can say their orders are 2a1 up to 2a half of t plus 1. And then if we just consider these numbers, t plus 1, then pigeonhole theorem says there's partial sum aj, which is a multiple of that one. So then 2aj must be multiple of t plus 1. But in our case, n is just 2t plus 1. So twice of this is impossible. That means this should be really t plus 1. So that means this component makes a part of size t plus 1, which is separated from the other part. So G kind of is this kind of graph. That's a contradiction. So considering these two, we deal with the case where G does not contain any tree component of odd order. And after this one, if you have a tree component of odd order, then we will use some transformation to get rid of those components. And then the case will reduce to this case. So suppose there is no tree component of odd order, then all the tree components are even orders. So then with these two inequalities, you have this many tree components of even orders. And I solved out each case separately. So if there is a half of t minus 5 tree components of even order, then we said there might be 2 more even parts, because the number of tree components of even order is at most half of t minus 1. So then we have 2 more possibilities. And also in this case, we have enough tree components, then all the other component is unicyclic. So all the other components are unicyclic of even order or odd order. Those are FE components or H components or O components. So then FE components make even part. And whenever you have 2 odd components, you can consider them together, those will make an even part. So you have these many more even components. That's almost 2. And also, if you consider independence number of a graph, that's almost t minus 1. And in the previous lemma, the unicyclic component is almost that order is 1. And the tree component is at least this much. So then if you add up these i's for all the components, then ig is half of order. And whenever you have FO components, you have one more number here, because IFO is plus 1. So whenever you have FO components, you have one more here. So that might be a number of FO. And IH is that one. So whenever you have H component, you have one subtracted there. So it will be like that. So then you have 3 unknowns here. Number of FE and number of H, number of FO, and 2 equations, but those numbers are integers, so you have only some possibilities. So we'll consider a simple case where there is no unicyclic component, F component, and the number of H component is 5. In that case, there is only 3 components of even orders, so then the orders sums up to at least t minus 5, because we have half of those components. And the H component, and I'm sorry, this graph has only 3 components and H components, so then 3 components, the order of 3 components is 2t minus plus 1 minus the order of H components. And each H component is a list of order 3, so that will make up this inequality, which is less than 4 times 3 component numbers. And also, we can consider the order of H components. So that would be the answer. And H component is because TG is at least this one. You can have this equation. And there are 5 over H components. So then if we just consider first 2 components, there should be at least 6 and at most t plus 1. Actually, this is even at most t minus 3. Because if you subtract t plus 6, if you subtract 9 from t plus 6, you will get t plus 3. And now t plus 1 minus this one is, by this equation, is t minus 5. That's actually almost the order of 3 components. Then by the pigeonhole theorem, that one is going to be the order of some partial sum. Then if you unionize these components, that will make a part of order t plus 1. So again, you have their kind of things. So you'll get a contradiction. Okay. And in the other cases, you can do similar jobs which are more complicated. And in the next case, when there are there are only half of t minus 3 components of even order, there might be some dual cyclic component. So you consider L and R and S instead of H and FO and FE. So you will get similar forms of equations and you can solve out.
Dual cyclic means cyclic?
You have 2 cycles in the graph.
3 plus 2 edges?
Yeah. Yeah. 3 plus 2 edges. When you have a 3 component of odd order, you do use this kind of transformations. So let's say that 3 component has order k, and you should have a non-3 component because otherwise your independence number is too big. So you say that B is a non-3 component of order L. And then the transformation goes like that. If T is K1, then you remove an edge of B which does not disconnect B and insert an edge joining T and that new component B minus 1 edge. So if you have this one and B, then what you do is you subtract one edge, B minus 1 edge, which does not disconnect B and 1. And that one has order L, so this new component has order L plus 1. It might be a 3 component of odd order, but L plus 1 is not 1 anyway. In the second case, if K is at least 3, you have T and B, then there's K and L, so then you get this one. K is odd. Okay, I'm sorry, I didn't mention it. If B is not a unicyclic component of odd order, you do this one. I'm sorry. If B is a unicyclic component of odd order, you do this one. So L is odd. So that's even. So it's not a 3 component of odd order. If B is not, then you change it to CK and you change it to B minus 1 edge, which does not disconnect BL. So again, there is no 3 component of even order, odd order. So even if you have K1, you do this transformation. After then, you apply these transformations. So by repeatedly applying these transformations, you get rid of all those 3 components of odd order. And then you can solve out the problem by the previous case. Okay. Let me give you the answer for the next problem, which is Brody and Mellendorf's problem for the instance n is 2t plus 1. Okay. So let me introduce some notations. When G is a graph, bridge is a cut edge. So if you subtract that edge, the graph is going to be disconnected. And cut vertex is a vertex. If you remove it, the graph is going to be disconnected. And G is 2 connected if it does not contain a cup vertex. That means you need to subtract at least 2 vertices to disconnect the graph. And block is the maximal connected subgraph, which is 2 connected. When the component is 2 connected, you have some lower bound of its independence numbers. Okay, I say that by using the result of previous problem, I could solve out this problem.
Can you show us the lower bound again? The lower bound of the independent of the 2 connected graph?
That one. I use the yield decomposition.
What is A?
A is order of the components. So this problem is like Ig is less than T and G does not contain TT this time. And our previous problem was, for that case, Ig is like that, and it does not contain T plus 1, like that. But if G does not contain this kind of graph, of course G does not contain this kind of graph. So then the minimum number of H here should be at least the minimum number of H here. And that was 7 when T is odd. So what I tried is try to consider all the extremal graphs here and then show that it does not satisfy this condition. So, and after that, fortunately, I could find out that this number is actually the next number. So this was by luck, I guess. So suppose G has that many edges, then the only candidates are those extremal graphs for the previous theorem. Suppose, okay, one more thing, sorry. When G is of this simple form, if you subtract one vertex from T6, you can subtract any T6. So you can divide this T6 into any order you want. Okay, if you have T6, and this really says you have this kind of components, so you have one more vertex here. So if you subtract x from here, then you can divide it into 2 parts. So T minus x is A and B, and A plus B is 5. So one is odd, one is even. So whenever you have odd components, okay, and you can add K3s as much as you need to get a component of order T. So in that case, G contains an induced union of subgraphs of order T and T. That case was simple. And in the other case, when G is of that form, now A was tricyclic, so it has MS3 blocks. And if A itself is a block, which means A is 2 connected, then IA is too big by the previous lemma. Otherwise, A has a cup vertex, x. If A minus x contains an odd component, then odd component x, then we will make a part which is of order t. So then in that case, what happens is you have x and some component of order t and the other component of order t. So you contain that kind of graph. So we should assume that A minus x does not contain an odd component. And I forgot one thing to mention. A does not contain a bridge, because in that case also if you subtract a vertex of which is a vertex of the bridge. So if you contain a bridge, x and y, and is y. That's odd number, so you may say that what? X is even. Then x minus x is again odd. So you contain an odd component. So then by this case, the graph contains that kind of separable subgraphs. So now the remaining cases are only the case where you have x here, then you have a block and block here, or you have 3 blocks meet at x. So if only 2 blocks of A intersect at x, then because we have only 3 cycles in this graph, one should be really a cycle because of ear decomposition, and the other one is previously dual cyclic. And in that case, you consider the independence number of those, and you get a contradiction. If you have 3 blocks meet at x, those 3 must be all cycles. And in that case, also, your independence number is too big. So those extremal graphs don't satisfy the conditions of the theorem. So then the next possible number, we hope, is that one. And we could find out examples for that numbers. So these are the examples. Okay, let me give you the answer for the last problem. And G does not contain tricyclic subgraph. Okay, and again, for this problem, I consider the first condition first. Then by Turan's problem, that should turn out to be 2t. This time n is 3t. So if you divide into t minus 1, you have 3. So the extremal graph is like 3k4 union t minus 4 k3. And E is 3t plus 6. Now, we consider 3 cases when t is equivalent to 2 mod 3. This graph satisfies this condition, so that's the answer. And this is the only extremal graph. And when t is 1 mod 3, this does not satisfy these conditions. So we try to modify this graph. And actually, what happened is we have K4, each one is 1 mod 3. So if you put K4s in different parts and add K3s, this makes trisectable graph. Now what I did is just to connect these two together. If we put only K3s, then this part, the order is 2 mod 3, so it shouldn't be T. And if you put that one, that is 0 mod 3, so it shouldn't make up order T anyway. So by just joining these two components, we could make a graph which is not trisectable. So there I got the number for E is 3t plus 7. That one, the answer is sorry. And I could prove that these are really the minimum numbers. And I could find out those examples, those extremal graphs also. Thank you.